Of all the planets, Venus is the one our ancestors knew best, for it is the brightest. After the sun and the moon, no natural object in the sky outshines it, a brilliant white lamp that hangs in the west after sunset or rides before the dawn, the evening star and the morning star of 100 mythologies, bright enough to cast a faint shadow and to be glimpsed, by a keen eye, in full daylight. That brilliance is the first clue to its nature, for it shines so because it is wrapped, pole to pole, in an unbroken deck of cloud that reflects 3/4 of the sunlight falling on it. And beneath that beautiful veil lies one of the most hostile places in the solar system, a surface, hot enough to melt lead, crushed under an atmosphere 90 times heavier than our own. Venus is Earth's twin in size and in substance, and its opposite in fate, the cautionary tale of how a world very like our own can go catastrophically wrong. Venus circles the Sun in the most nearly perfect circle of any planet, its distance varying by barely 1 part in 100, at a little over 7/10 of the Earth's distance from the Sun. But its turning is the strangest in the solar system. Venus spins backwards, in the opposite sense to its orbit and to almost every other planet, and it spins with extraordinary slowness, taking 243 Earth days to turn once on its axis, longer than the 225 days it takes to go once around the Sun. On Venus, in other words, the day is longer than the year, because the spin runs backward. The Sun, were you ever able to see it through the clouds, would rise in the west and set in the east, once every 117 Earth days. Its axis stands very nearly upright, so Venus has no seasons, only its single, unvarying planet-wide heat. In its body, Venus is the most Earth-like of all the planets. It is only 5% smaller than the Earth in radius, some 4/5 of its mass, and almost exactly as dense, which means it is built of the same stuff, rock over a large iron core, a sibling world formed from the same material at a neighboring distance from the Sun. By every measure that a scale or a ruler could take, Venus and Earth are twins, and yet almost every feature of their surfaces and their skies has diverged, utterly and catastrophically. One world stayed cool and wet and grew a living biosphere, the other became a furnace sealed under crushing cloud. Explaining that divergence, why two planets so alike, at their birth should have ended so differently, is the central scientific problem that Venus poses, and it is not a question about one planet only, but about what it takes for any world to remain a place where life could live. The furnace is real, and almost beyond imagining. At the surface, the atmosphere presses down with about 92 times the weight of Earth's air at sea level. The pressure you would feel nearly a kilometre deep in the ocean, and the temperature holds steady at some 737 Kelvin, around 460 degrees Celsius, hot enough to melt lead and tin and zinc. And because that dense atmosphere carries heat so efficiently around the globe, the temperature scarcely changes at all, not between the equator and the poles, not between the long day and the long night. The air at the surface is so dense, more than 50 times denser than the air we breathe, that it behaves almost like a fluid, a hot, sluggish ocean of carbon dioxide. There is no hotter planetary surface anywhere in the solar system, not even on Mercury, which sits twice as close to the Sun. What makes that atmosphere so deadly is chiefly what it is made of. It is overwhelmingly carbon dioxide, some 96.5%, with most of the small remainder being nitrogen. And though nitrogen is only a few percent of the mixture, there is so much atmosphere in total that Venus holds several times more nitrogen than the whole of Earth's air. Traces of sulfur dioxide, water vapor, and other gases make up the rest. The atmosphere is vast, about 90 times the mass of Earth's, and it thins only gradually with height, through a deep lower layer where the greenhouse and the winds live, up to the cloud tops and the tenuous haze above. Curiously, there is one altitude, around 50 kilometers up, where the pressure falls to roughly that at Earth's surface and the temperature to a survivable few tens of degrees, the single most temperate spot on the planet, and the reason some have wondered, speculatively, whether the clouds might offer a niche for airborne microbial life. The clouds themselves are the source of the planet's blinding brightness, and they are made not of water, but of concentrated sulfuric acid. A continuous deck of acid droplets wraps the planet between roughly 50 and 70 kilometers up, with hazes reaching higher and lower still, and it is this bright reflective shroud that hurls 3/4 of the incoming sunlight back into space and makes Venus shine so fiercely in our sky. The clouds are perpetual and global, they never part to show the ground, which is why for centuries Venus kept its secrets, and why some once imagined a warm, swampy, oceanic world beneath. The reality is a sky of acid, forming high up where ultraviolet sunlight breaks apart carbon dioxide and sulfur dioxide and drives a chemistry that builds sulfuric acid, which condenses into droplets, drifts downward, evaporates in the fierce heat below, and rises again to begin the cycle anew. A closed, self-sustaining engine of acid that has veiled the planet for as long as we have watched it. The clouds hold two enduring mysteries. In ultraviolet light, Venus is not blank but marbled with dark streaks and a great planet-spanning letter Y, the mark of some substance high in the clouds that drinks up ultraviolet sunlight, soaking up nearly half the solar energy the cloud region absorbs and so helping to set the planet's whole heat balance. What that unknown absorber is after decades of study, no one can yet say for certain. The second mystery is sharper and more contested. In 2020, astronomers reported traces of phosphine in the clouds, a gas that on Earth is linked to life, and the claim caused a sensation. But it was quickly disputed. Later analyses argued the signal could be explained by ordinary sulfur dioxide or by quirks of the data, and the detection remains unconfirmed and controversial. It is a textbook lesson in caution. A possible sign of life on another world must be treated as an open question, to be doubted and retested, until far stronger evidence can settle it. Why is Venus so hot? Not simply because it is closer to the Sun, for its brilliant clouds throw back so much sunlight that Venus actually absorbs less solar energy than the Earth does, and by rights its surface should be colder than ours, a little above 200 Kelvin. The 737 Kelvin it reaches instead represents a warming of some 500 Kelvin, by far the mightiest greenhouse effect in the solar system. The mechanism is the one now infamous from our own concerns. The thick carbon dioxide atmosphere, with its clouds and its traces of water vapor, is nearly opaque to the infrared heat the surface tries to radiate away and traps it below. But Venus shows the effect in its most extreme and terrifying form, the runaway greenhouse. There is a fundamental limit to how much heat an atmosphere thick with water vapor can shed to space. And if a planet absorbs more sunlight than that limit allows, no cool, stable climate is possible at all. When that threshold is crossed, the consequences are irreversible. As the surface warms, more water evaporates. Water vapor is itself a powerful greenhouse gas, so the warming feeds upon itself. The oceans boil away entirely into a thick blanket of steam, and the surface temperature climbs to many hundreds of degrees. This, the leading account holds, is what befell Venus, and though its oceans are long gone, they left a fingerprint behind. In Venus's atmosphere, the ratio of heavy hydrogen, deuterium, to ordinary hydrogen is enriched about 120 times above the Earth's, exactly what one would expect if a vast reservoir of water had been broken apart by sunlight and the lighter hydrogen had streamed away into space, leaving the heavier deuterium behind. From that ratio we can read that Venus has lost all but a tiny fraction of its original water, an ocean perhaps hundreds of meters deep, boiled away and scattered to space across the ages. Venus is the solar system's great cautionary tale of a climate catastrophe, written in the isotopes of a vanished sea. That escape of hydrogen was helped by another of Venus's deficits. It has no magnetic field. The Earth's molten, churning core generates the magnetic shield that deflects the solar wind and protects our air. Venus, with an iron core almost the same as ours, generates nothing. The reason seems to lie not in the core itself, but in how the planet sheds its heat. Earth's shifting tectonic plates carry heat efficiently up from the depths, keeping the core stirring. Venus, as we shall see, has no such plates, and so its interior heat builds up beneath a stagnant shell until the churning that would drive a magnetic dynamo falters and dies. Left unshielded, the top of Venus's atmosphere lies open to the solar wind, which strips away its lightest gases, including the hydrogen and oxygen left over from that broken-apart water, into space. The planet's dead core, its missing field, and its lost ocean are not separate facts, but strands of a single story, each of them tied to the others. Beneath the eternal clouds, the surface of Venus was for most of history entirely hidden, until radar learned to see through them. The great revelation came from NASA Magellan orbiter, which between 1990 and 1994 swept the planet with radar and mapped more than 98% of its surface in fine detail, the map that founds Venusian geology to this day. What it found was a world shaped above all by volcanoes. Venus is the most volcanic planet in the solar system by sheer count of them. Thousands upon thousands of volcanic edifices, from broad shield volcanoes rising some 5 kilometers, to vast plains flooded by ancient runny lava, to a form found nowhere else. The pancake domes, flat-topped circular blisters up to 15 kilometers across, squeezed out of the crust like thick paste under the crushing weight of the atmosphere. Volcanism, more than anything else, has made and remade the face of Venus. Among the strangest of these volcanic features are the coronae, great circular crowns, some more than 1,000 kilometers across, ringed by rings of fractures and ridges. They are thought to form where blobs of hot, buoyant rock rise from the mantle and push up against the underside of the crust, doming it into a great blister that then collapses and cracks, spilling lava around its edges. There are hundreds of them, and recent study of the old Magellan data suggests that many sit above, upwellings that are still active today, still bleeding the planet's inner heat to the surface. Perhaps the nearest thing Venus has to the slow churning that, on Earth, the moving plates provide. If so, the coronae may be where Venus does its own peculiar version of the work that plate tectonics does for us, not sliding great plates past one another, but blistering and recycling its crust in rings, hundreds of them scattered across the planet, each marking a plume of heat rising from below. Whether Venus is volcanically alive today, and not merely in the recent past, was for decades an open question, until a discovery in 2023 settled it. Re-examining Magellan's own radar images, taken across 8 months back in 1991, scientists found a volcanic vent on the flank of one of Venus's great volcanoes that had visibly changed between the two passes. It had grown and altered its shape, most plausibly because it had erupted in the interval. It was the first direct, geological evidence that Venus is volcanically active now, in our own time. Further searches through the old images have since turned up more candidate changes, more likely lava flows caught in the act, and the balance of opinion has swung firmly to the view that Venus is an active planet, its volcanoes not extinct monuments but living vents, erupting still beneath the clouds. Just how often and how much remains to be measured, and it is a prime target of the missions now being built. For all its volcanism, Venus wears a gentler face than the Earth. It has nothing like our sharp division between deep ocean basins and high continents, the signature that plate tectonics stamps upon our world. Instead, some 4/5 of Venus is low, rolling volcanic plain. Rising from it are two great highland continents, one in the north about the size of Australia, crowned by a mountain range whose summit stands some 11 kilometers above the average level, as high above it as Everest stands above the sea, the other, near the equator, as large as Africa. And scattered through the highlands lie the tesserae, regions of crust folded and cracked and refolded in every direction, the oldest and most tortured terrain on the planet, the surviving record perhaps of an earlier age, when the crust of Venus moved more freely than it does now, before the heat and the drought locked it into stillness. The radar maps also carry the key to the planet's age, in the form of its impact craters, and here Venus poses one of the sharpest puzzles in planetary science. There are around 1,000 craters, and two things about them are strange. First, there are almost none below about 2 kilometers across, because the immense atmosphere shatters and burns up smaller incoming meteoroids before they can reach the ground. Second, and far stranger, the craters are scattered almost at random across the whole globe, and nearly all of them look fresh and undamaged, as though the entire surface of Venus were the same age, and a young age at that, only a few 100 million years old, on a planet 4.5 billion years old. It is as if Venus had been repaved all over in a single geologically recent episode. Whether that happened in one catastrophic global overturn, or in some more gradual way, is a genuine and unsettled debate, but that the whole surface is young seems beyond doubt. If the solid planet turns with dreamlike slowness, its atmosphere does the opposite. High up at the cloud tops, the whole mass of air races around the planet in only about 4 Earth days, 60 times faster than the ground turns beneath it at a planet-girdling gale of some 360 kilometers an hour, all of it blowing in the same backward direction as the sluggish spin. This is the famous superrotation of Venus, and it is a genuine dynamical puzzle. Down at the surface the winds are gentle, only a few kilometers an hour, but the atmosphere as a whole spins far, far faster than the planet it clothes. Friction with the slow ground ought steadily to drain that spin away, and yet the great high-altitude winds are somehow sustained, year upon year, century upon century. Something must be continually feeding new spin up into the cloud-level winds to replace what the surface drags away, and identifying that something has been one of the long-standing problems of the planet's meteorology. The answer seems to lie in the rhythm of Venus's own heating. As the sun beats upon the clouds, It drives great atmospheric tides, waves of heating and cooling that sweep around the planet with the sun, and these, on so slowly turning a world, can carry momentum from place to place and pump the high winds. Japan's Akatsuki orbiter, watching the clouds since 2015, tracked their motions in ultraviolet light, and in 2020 showed that these thermal tides do indeed supply most of the momentum needed to keep the cloud-top winds spinning near the equator. The great atmosphere is organized into planet-spanning waves, the dark Y that stretches across the ultraviolet face of Venus, and into vast, ever-shifting vortices swirling over each pole, structures far more chaotic and changeable than anything in Earth's sky. In its winds and its vortices, Venus has become a natural laboratory for the weather of slowly turning worlds, including, now, the many such planets being found around other stars. Venus was the first planet humanity ever visited. In December 1962, NASA Mariner 2 swept past, and with its instruments confirmed that the surface was fiercely hot, dispelling the last dreams of a temperate world beneath the clouds. Then came one of the most remarkable feats in the history of exploration, the Soviet Venera and Vega programs, which set out to land on a planet that destroys everything sent to it. In 1970, Venera 7 became the first spacecraft ever to transmit data from the surface of another planet, surviving just long enough on the ground to report the crushing pressure and heat. Venera 9 in 1975 sent back the first photograph ever taken from the surface of another world, a bleak, rock-strewn plain. Later probes returned color panoramas of an orange-lit, stony desert, and 2 Vega craft even released balloons that drifted for days through the temperate cloud layer, riding the very super-rotating winds. Each machine died within an hour or two, roasted and crushed, having wrung its measurements from a world that suffered no visitors to stay. After a long lull, Venus is once more a destination. The single most important mission for the surface remains Magellan and its radar map. Europe's Venus Express studied the atmosphere through the 2000s, watching the polar vortices and the shifting sulfur dioxide. Japan's Akatsuki studies its weather still, and now a new fleet is being built for the coming decade. America's DAVINCI will drop a probe through the atmosphere to taste its chemistry directly, measuring the gases and the telltale hydrogen ratio that record the lost ocean and photographing the surface as it descends. Its sister mission, VERITAS and Europe's EnVision, will circle Venus with a new generation of radar and spectrometers, mapping the surface far more sharply than Magellan ever could, hunting for the heat of active volcanoes and the fine detail of the tortured crust. Between them they are designed to answer the very questions this chapter has had to leave open: how much water Venus once had, how it was lost, whether the surface still stirs, and what the clouds are truly made of. Step back and Venus is best understood as a great controlled experiment, a planet born Earth's twin, and made its opposite by its circumstances. The decisive difference seems to have been sunlight. Venus receives about twice the solar energy the Earth does, and that extra warmth appears to have pushed the young planet across, or perilously close to, the runaway-greenhouse threshold, boiling off its water. And the loss of that water, in turn, may have stiffened its crust and helped to shut down the plate tectonics that might otherwise have cooled it. And here the deepest link of all emerges. Without moving plates, Venus has no way to draw its carbon dioxide down out of the air and lock it into rock as the Earth continually does. The carbon that on our world lies buried in vast beds of limestone instead hangs in Venus's sky as those crushing 92 atmospheres of gas. Earth's temperate climate, it turns out, depends on quietly, endlessly recycling its greenhouse gas into stone, a thing that Venus cannot do, and so the importance of Venus reaches far beyond itself. As we discover thousands of planets around other stars, many of them rocky worlds sitting near the warm inner edge of their stars' habitable zones, Venus stands as the only close example we have of what such a world can become, a planet that had every chance to be another Earth and lost it. Its scorched surface and its poisoned sky are the calibration for our models of which distant worlds might keep their water and which will lose it, the empirical anchor for reading the light of Earth-sized planets we may never visit. To understand why Earth's twin became a furnace sealed in acid is not, in the end, a question about one planet only. It is a test of whether we can tell, across the gulfs of space, the living worlds from the dead ones, and perhaps in the warning written across the face of Venus, a lesson worth heeding on the one temperate world we know.